We'll begin our discussion on waves by first talking about transverse and longitudinal waves. See, a wave allows energy to be transmitted from one point to another point which is some distance away. Without the particles of the medium, the medium has particles over here. Without the particles of the medium actually traveling between the 2 points. Let's look at this statement a little more in detail. Okay, now just tell me something. Say you're standing here and your friend is standing here. Now, as you shout out to your friend, sound waves are carrying energy from A to B. Suppose you jerk this end of a string. Let me just draw this. You can actually watch waves travel as you shake one end of the stretched string up and down. You would be moving your hand in this direction. And the string, you can see these waves which are created and they move towards the other end. Now these waves carry energy from a point over here A to a point over here at B. Now let's notice something important in these two examples. See, energy travels from A to B. But do the particles of the medium also go from A to B? Does the string over here after some time reach this point? Or does the air which is present over here after some time reach this point over here? Think about this a little. Okay, now both these are examples of mechanical waves. By mechanical waves, we mean waves that require a medium. We said that only energy is transferred from one point to the other, but the particles of the medium that were at A do not move and reach the other point B. Now, does this mean that the particles of the medium do not move at all? No, that's not the case. See, the first one is a longitudinal wave. The sound wave travels as a longitudinal wave, and these waves along the string travel as transverse waves. Now, what is the difference between a longitudinal wave and a transverse wave? In this case, the vibrations of the particles of the medium are vibrating in this direction. The vibration of the particles of the medium is same as the direction of travel of the wave. The arrow that I have drawn over here shows the direction of travel of the wave, and the direction of the particles of the medium is also in the same direction, the direction of motion of the particles of the medium. Whereas if you look at a transverse wave, the direction in which the wave travels remains the same. The wave is traveling in this direction, but the particles of the medium are moving in a direction perpendicular to the direction of travel of the wave. So this is the direction of travel of the wave, and this is the direction of motion of the particles. So you can see in case of longitudinal waves, the direction of travel and motion of particles is the same, and sound waves are a typical example of longitudinal waves. In case of transverse waves, the direction of travel and motion of the particles is perpendicular to each other, and a typical example of a transverse wave can be waves in a stretched string or electromagnetic waves. See, in case of electromagnetic waves, there are no particles of the medium, but we have an electric field and a magnetic field which is perpendicular to the direction of travel. So, say this is the electric field, this is the magnetic field, and this is the direction in which the wave travels. All our discussions will hold true for electromagnetic waves also, but we will be talking of the particles of the medium and we will be talking about mechanical waves because it's easier to understand the description in terms of mechanical waves. Now let's look at transverse waves a little more in detail. The perpendicular ones. Okay. Now you know that what the movement of these particles reminds me of? Say you're standing in a stadium and you're watching a cricket match, or let's say a concert, and let's say you're standing here or sitting here and you have your friend over here, and there are a lot of people in the stadium, and then you want to really cheer the players, and the crowd makes a wave. So what happens? So to make the wave, so when it's your turn, you stand up and then you sit down again. Now your friend who's a short distance away, let's say the wave is traveling in this direction, your friend who's a short distance away does the same. After a short while he stands up and then he sits down. You don't have to run in the stadium. You have to remain in your seat, you have to remain in your position, but you have to stand and sit when the wave passes you. Now each particle in the medium seems to be doing the same. They are also playing the same game. See, the particles can't think like you, or you can't tell them to move. So they move only when they experience a force. So when the particles of the medium experience a force by the adjacent portions of the medium, for instance in this stretched string, when it moves, let's say this, you jerk this end upwards. So when it moves upwards, it pulls the adjacent portions of the string also in the upward direction. It pulls it through the tension. So if there is no tension in the string, if the string is slack, in that case there will be no movement. The wave will not propagate. Next we'll write an expression for the velocity of the waves. This expression is V is equal to frequency times the wavelength. Now let's see how do we arrive at this relation. See, if you notice something, there is something interesting happening over here. The frequency with which the particles of the medium are vibrating is the same as the frequency of the source that produces these waves. Now let's say the frequency is f. So the frequency with which each point on the wave or each point in the medium moves is also f. In that case we say that the frequency of the wave is f. Now when the source vibrates once, then the waveform moves forward through a distance which is the wavelength lambda. So if the source vibrates once, the wave moves forward through a distance lambda. Now if the source vibrates f times, the wave moves forward through a distance lambda times the frequency. Now this means the wave moves forward through a distance of lambda times f in 1 second. So you can say that the velocity of the wave, velocity is distance upon time. In this case distance is lambda times f and the time is 1 second. So in this case the velocity of the wave becomes lambda times the frequency of the wave. Now let's take a look at longitudinal waves. I'll just draw particles to show how longitudinal waves propagate. Let me just draw this. Maybe you can also draw this along with me. It will give you a better understanding. We are talking of longitudinal waves like sound waves. So I've just drawn a grid over here to mark particles at equal distances. So this is a rarefaction, then we have a compression over here, we have a rarefaction. See, at a compression the particles are being pushed close together. At a rarefaction the particles have moved away. So we have alternately we have a compression and a rarefaction. See, in a compression the particles are being pushed towards this point. So let's say we have a few points over here which are close to the center and the particles are being pushed in this direction towards the compression. Okay. Now in case of a rarefaction, say we have a particle over here, the particle is being pushed away, which means the particle is moving in this direction. It's going towards the right, away from the rarefaction. Again, if you look at the rarefaction over here, the particle has moved away from it. Maybe we can draw another particle over here. That particle will move away from this rarefaction. We have a particle on this side that is also moving away from it, which means it is moving towards the compression. Once again, particles are moving towards the compression. So you have particles which will be close together at the compression, and particles are moving away from the rarefaction. So this particle is moving away. Again, if we have a particle over here, it's moving away. Particles are moving towards the compression. Now we want to draw a wave to denote this. So what we are going to assume is, if particles move in this direction, we denote that above the axis in the positive direction, and if the particles move in the opposite direction, we take that as negative, so we show it below the axis. Now since the particles in this region, you can see that the particles are not moving at these points, at the centers of the compressions and the rarefactions. So at this point we have zero displacement. Here they are moving towards the right. In this region the particles are moving towards the left. They are again moving towards the right. They are moving towards the left, moving towards the right, moving towards the left. Okay, so now this is the wave that we have drawn, and you can see that the sine wave is representing a longitudinal wave, though there is no motion in this direction, but still we are drawing a sine wave to represent this wave, because the displacement of the particle in the horizontal direction is shown above the axis and below the axis. Now after half a cycle, we have a rarefaction which has moved here. Now a compression at this point where we earlier had a rarefaction here, a compression here. I have not drawn this. Over here also we'll have a compression, rarefaction and a compression. So if it's a compression, you know the particles will be moving towards this point. If it's a rarefaction, you have the particles moving away from it. If it is a compression, particles moving towards the compression, particles towards the compression. In case of a rarefaction, they move away. Now showing the displacements in this direction, the negative direction, by a negative wave like this, because this is a negative displacement, and this would be the other half, and you can once again draw the wave. So now you can see that we are drawing a sine wave which changes or which travels in the forward direction. So it is called a progressive longitudinal wave. You can continue to draw the wave. Next we'll again have rarefactions here, compressions here, rarefactions, compressions. So once again you have waves traveling away from the rarefaction towards the compression, in this case away from the rarefaction, and you can again draw a wave after half a cycle which would look like this. So this is, say, at time t0, this is at half a cycle, and this is at a full cycle. So you can see that we are back to what we started with. You could also draw some intermediate states at, say, t by 4 and 3t by 4. Now if you look at this graph over here, this graph that we've drawn shows the displacement. You could have also shown the pressure. If you draw a pressure versus x graph, that would look like this. See, at a compression we would have a high pressure region. At a rarefaction we would have a low pressure region. Again at a compression, high pressure. At a rarefaction, low pressure. Notice that this is normal pressure. Over here you don't have positive and negative pressure. You have, this is normal atmospheric pressure, above atmospheric pressure, below atmospheric pressure. Since the molecules are close over here, the pressure is high. Since the molecules are far apart, the pressure is low. And this would again be a low pressure region. So you would get a graph which looks like this. To test your understanding, just try these questions. You have to complete the given statements. And here are the answers.